All right, so momentum and impulse. Definition of momentum is it is the product of an object's mass and the object's velocity. Okay, again, it's the product of an object's mass and velocity. And so when you hear the word product, it is the product of an object's mass and velocity. What do we mean by product? You can go ahead and type your answer in the chat. What do we mean by product? The product of an object's mass and velocity. Okay, so it's actually, product means you are multiplying. You multiply, all right? Product is multiply. So the equation for momentum, where P stands for momentum, that's a lowercase p, equals mass times velocity. Okay, yes, you are multiplying, all right? So product means you multiply. Momentum is mass times velocity, the product of mass and velocity. So normally when you hear, what are some examples as where you would use the term momentum? What are you talking about when you use the word momentum? Some examples in the chat. What is an example of momentum? Okay, so I see running a bit before jumping, running downhill. So in all of these, you're talking about you have to be in motion. A ball being thrown. A segue into something else. You use it in dance. Cars, motions before collision. So if you have something that, if you're talking about, here's my question. Okay, so if I throw a baseball and it is moving at, let's say, it's just a soft throw, 2 meters per second, but you also have a train that is moving at 2 meters per second. Which one of those would have more momentum? The train. Okay, so do you think that something with more momentum would be easier to stop or harder to stop if it has more momentum? It's going to be harder to stop, all right? So it's just like even if you are driving a car, the faster you're going, the more momentum you have. You could be driving the same car, okay? I'm going at, down the street at 10 miles per hour versus going down the street at 50 miles per hour. The faster you're going, the more momentum it's going to have, so that if you hit those brakes hard, because it has more momentum, it's going to take it longer to stop, right? So things with a lot of momentum are harder to stop. It has to do with your velocity, okay? So the faster you're going, the more momentum you have, and it is dependent on your mass. So the bigger something is, the faster something is, the more momentum it is going to have, all right? This is like one of those reasons why if you're on the freeway and you have one of those rigs, the 18-wheelers that are behind you, and they're going just as fast as you are and they're really close, it's kind of scary because think about it. If you have to stop really quick, are they going to be able to? That rig that's behind you? No, they're not going to be able to stop, not as quickly. So that's why even when you're just driving, it doesn't have to be an 18-wheeler. That's the reason why you want to make sure that you keep your distance. Y'all are going to be driving soon if you're not already driving. So you want to keep distance between you and the car in front of you, okay, so that what happens is, and if you have to stop quickly, remember that because of momentum, you're not going to stop immediately. It's going to take a little time for you to stop. So that's why you want to have a gap, some distance between you. The faster you're going, right, the more distance there should be between you and the car in front of you. All right? Okay, so momentum, mass times velocity. The units for momentum are, so momentum, mass is kilograms times meters per second. Kilograms for mass, and this is times meters per second. Now, normally what happens is for momentum, you will see it written as a Newton second, a Newton second, okay? But if you were to break down these units, let me go ahead and do that for you. Let's take a look at what happens when we simplify this, remove any units that we can. Okay, so it says momentum normally is, if I was to write something for momentum, I'd say momentum is, let's just number, if I see 30 Newton seconds written down, that is momentum for whatever object you're talking about. All right, so anytime you see units Newton seconds, that is momentum. Well, let's go ahead and break this down and simplify it. Let's see what we can get rid of. A Newton breaks down into what? So think about Newton. Newton is a unit of measurement for force. All right, so what does a Newton break down into? What is a Newton made up of? Joules has to do with energy. So Newtons is force. Think about the equation. Newtons is a unit measurement for force. Force equals what? What's the equation? Mass times acceleration. So you have kilogram. A Newton is a kilogram times, what are the units of measurement for acceleration? What are the units of measurement? Good, meters per second squared. Okay, so let me plug this back in here. I'm just breaking this down. So I have a kilogram times meters over second squared for the Newton, but then I have times seconds. This is like seconds over 1. So when I cancel things out, I'm going to cancel out one of the s's here, one of the seconds. I'm going to end up with kilograms times meters per second. Okay? So Newton breaks down into kilograms times meters per second squared. And then you have that times a second, which is seconds over 1. If I cancel out one of these seconds, okay, because there's seconds squared on the bottom and seconds on top, I end up with kilograms times meters per second. All right, so that is what this is. It's mass times velocity. Okay, so when you are calculating your momentum, I will take either one of them. Normally, this is how the units of momentum are written. But if you decide to write instead of 30 Newton seconds, you decide to write 30 kilograms times meters per second, I will go ahead and take that. All right, because they are equivalent to each other. Okay. Are there any questions on this part so far? All right, so now that is momentum. Momentum is going to be your mass times velocity. So if a train is sitting just on a track, it's not moving, how much momentum would it have? How much momentum would it have? Good. It's going to have 0 momentum. No momentum because you have to be in motion. Okay, velocity has to be something other than 0 in order for there to be momentum. No velocity, not moving, at rest means no momentum, or momentum is 0. All right, so next one is impulse. Impulse is the product of the average net force. Product, again, that means you are multiplying. Product of the average net force, which we have abbreviated as F net, on an object Okay, product of the average net force and the time interval which means your delta t, over which the force happens. product of the average net force on an object and the time interval, which is delta t, over which the force happens. Okay, so the equation for this, and I didn't leave any room over here, so I'm going to put it over here. The equation for impulse is, now it kind of depends on what resource you're using as far as what they use for the symbol for that variable for impulse. So I'm going to use the ones that I've seen most common, and that's J. J stands for impulse, capital J, and it is going to be, again, your force times your change in time, F delta T. All right. Your force times your time. Again, look at the units. So what are the units of force? What is the unit of measurement for force? All right, so as far as the units of measurement for force, it is newtons, and then your change in time, your delta T, what would that be? What are the units for delta T? Seconds, thank you. All right, so that means you have Newton second, which is the same, these are the same units that we just used for momentum, okay? All right, so impulse and momentum use the same units of measurement. So that leads us to the impulse momentum theorem, which says the impulse of an object equals the object's change in momentum. The impulse of an object equals the object's change in momentum. So that means your equation is now, they can be set equal to each other. We have impulse, which is F. Okay, let me write it this way. Your impulse equals your change in momentum. That's simply put, and now we're going to break it down. So as far as your impulse, it's F delta T. Change in impulse means you have a final and an initial. So the equation for impulse is m times v, but since we're talking about change, that means you're going to have your mv final. Okay, that's your final momentum minus mv initial. All right? Impulse equals change in momentum. Okay, if you need me to add another step in there, that means impulse equals P final minus P initial. And then this is the breakdown for it. So the final equation is this, if you're breaking it down into the pieces. Okay? This is simplified, and then breaking it down into what that means. Change in momentum means momentum final minus momentum initial. When you break those down, momentum is mass times velocity, so mass times velocity final minus mass times velocity initial. Does anyone have any questions on this part? Okay, so you have basically three equations you're working with. You have the equation that is just for momentum. You have an equation that is just for impulse. And then you have the impulse momentum theorem that combines the both of them. All right, now, so what happens is which equation you use is going to be dependent on your list. Okay, what information are you given to work with? All right, so you may be given enough information, you may be given mass and velocity and asked to solve for momentum. You may be given the change in time and the force to solve for impulse. You may be given a combination. Maybe you're given a force and you're given a change in momentum and you're asked to solve for the time over which that happened, okay? So again, you make your list first and then compare to the equation, see which one you can use, what you're trying to solve for. Okay, so let's look at this first problem. How does magnitude of force affect momentum? So practice problem. Oh, that was a question. This is actually separate. So how does magnitude of force affect momentum? How does the magnitude of the force affect the momentum? What do you think? So if you're answering something like that, how does the magnitude, the size of the force, affect the momentum? Magnitude of the force, remember force is in your impulse, how does it affect momentum? So think, something you would answer is like, if you increase, so it's almost like a hypothesis, if you increase force, then, or if you decrease force, then, so what would you, let's go with the increase. If you increase force, then what do you think that's going to do? Directly proportional, so what does that mean? Let's be a little bit more specific. If I increase force, what is that going to do with momentum? You're going to increase the momentum, okay? Increase the momentum, okay? So when you are answering, make sure you're using the terms that are in the question, okay? Yes, if you increase the force, you are going to increase the speed. All right, but the question still is asking, how does that affect momentum? So velocity is in momentum, okay, but you need to say that directly then. So if you increase the force, you can say if you increase the force, it increases the speed, which increases momentum, all right? Or you can just directly use those two words. So if you increase force, then momentum will increase. So I'm gonna go ahead and put they are directly proportional. But then again, you need to explain, what does that mean? If force increases, and I'm going to abbreviate that with an arrow, then momentum will increase. Then momentum increases. You could add another sentence. If force decreases, then momentum decreases. Okay, so the question, as far as the practice problem, it says a 1,350 kilogram car has a velocity of 22 meters per second to the north. When braking rapidly, it stops in 4.50 seconds. So in your list, we have mass equals 1,350 kilograms. We have it's moving to the north, which is positive. Direction is important here. We have it is moving at 22.0 meters per second. So if it's moving south, you're going to have to put a negative on it, all right? Later on, the next set of notes, we'll be talking about collision. So you're going to have things that may be heading in opposite directions. So actually, even in, no, it's not in this one, in the next set of notes, all right? So if the direction is different, you need to account with that with positive and negatives. So this is moving north. It says when braking rapidly, it stops in, so that's your delta T, 4.50 seconds. Takes 4.5 seconds to stop. Two questions. What was the momentum of the car before braking? So you're looking for your momentum initial. And then it says, what is the magnitude of the force required to stop the car? So you're looking for your F. All right, so looking at your initial momentum. Remember, initial momentum, momentum is mass times velocity. It's mass times your initial velocity. So momentum initial equals mass times your initial velocity. Please, 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 if you have questions, ask. Ask out loud or put it in the chat. If you need something clarified, please let me know. Okay, so plug in your numbers. Your mass is 1350. And your initial velocity is 22.0 meters per second. So 1350 times 22. Big number, use scientific notation, is 2.97 times 10 to the fourth kilograms times meters per second, or Newton second. Kilograms times meters per second, or Newton second. All right. Does anyone need a refresher on how to write scientific notation? Say so now if you do. Okay, so let's review this. Okay, so when you're looking at a standard number, so let's say that, let's say it's 297,000, and you are to write this in scientific notation. Okay, so the way this works is you are going to have a coefficient, which is the number that goes out in front, times 10 to your exponent, okay? So you're going to have exponent here. Your coefficient has to be, let me see if I'm writing this right. Okay, so let's say your coefficient is x. It has to be less than 10, but it's got to be, it can be greater than or equal to 1. Is that written right? Okay, so your coefficient, which is the x, is basically between 1 and 10, but it can't be 10. It can be 1, but it's got to be less than 10, so 9.9, all right? So when you're looking at a standard number like this, think of it this way. Where would I have to put the decimal to make this number between 1 and 10? Where would the decimal have to be in this number to make it between 1 and 10? That's a question for y'all. Thank you. 2.97. So it's going to have to be right here. So that will be my coefficient, because the coefficient has to be between 1 and 10. But this is not the original number. 2.97 is not equal to 297,000. So I am going to multiply it by 10. How many times do I need to multiply it by 10 to make it 297,000? Okay, so remember when you were multiplying by 10? Okay, so let's say I start out with 1. 1 times 10 is what? 1 times 10 is what? 10. 10 times 10 is what? 100. 100 times 10 is what? 1,000. Okay, so if you notice, every time I multiplied it by 10, I multiplied it by 10. Basically what I'm doing is I move the decimal over one place. Does everyone see that? Okay, so here, when I'm multiplying by 10, I'm moving my decimal. When you are multiplying, you are moving your decimal to the right for every time you multiply by 10. Okay, so I just put my decimal here. How many times do I need to move my decimal to the right to make it the original number, which is 297,000? 1, 2, 3, 4, 5. You need to multiply it by 10 5 times. Good. So that is 10 to the 5th. Okay, if you are multiplying, you are moving it to the right. Okay, each space, each number counts as one space. So 1, 2, 3, 4, 5. Okay, all right, so anytime you are multiplying, you are moving your decimal to the right. Okay, I'm going to put a number up here, and I want you to write it in scientific notation. Let's say it is write that one in scientific notation. And put it in the chat, please. All right, to make this between 1 and 10, the decimal would have to be between the 3 and the 5. And then, yes, you have to move your decimal 2 places to the right, multiply it by 10 twice. Okay, good. 3.55 10 to the second. Now, what if it's a really small number? Let's say it's 0.0057. Still, what you're going to do is coefficient has to be between 1 and 10. So that means what's the coefficient going to be? What is the coefficient for this if I'm changing it to scientific notation? 0.0057. Because it still needs to be between 5 and 10. Good. So 5.7. Okay, so in this case, to get the decimal back to the original position, which is here, you're going backwards. You have to move. I put the decimal here, but I need to go backwards. That means you are dividing by 10. Okay? How many times do I need to divide by 10? 1, 2, 3. To show division with exponents, it's a negative. All right? So it's 5.7 times 10 to the negative 3. Go ahead and try this one. And then we'll move on. So write this one in scientific notation. Okay, good. 4.7, number of coefficients between 1 and 10, and then that means you need to go back or divide by 10 4 times. So times 10 to the negative 4 would be the answer. Good. All right, so let's go back to this work. So this was 2.97 times 10 to the 4th kilograms times meters per second. Again, you can write kilograms times meters per second or write Newton second. Okay, so next question, stopping time and force. When stopping, the change in momentum is the same for rapid or gradual stops, all right? So it doesn't matter if you're stopping, if I'm like, I'm moving 50 miles per hour and then I slow down over a long period of time, right? The fact is, if I started at 50 miles per hour, I am still going to 0, right? Your change in momentum has nothing to do with time. It has to do with your mass times, or you've got your final velocity and your initial velocity. No matter how long it takes me to stop, my final velocity is going to be 0, and I still started at 50 miles per hour. So that means your change in momentum is going to be the same no matter how long it takes to stop. All right. So it says increasing the time decreases the force, though. So even though my momentum here, my change in momentum does not matter, doesn't affect, my change in momentum is always going to be the same no matter what my speed is. Okay, how much time it takes me to slow down, if I stop quickly or if I stop slowly, all right, then what happens is my change in momentum is not going to change. So this number stays the same over here, but my delta t will change. So if I increase this number, what is that going to do to the force? Okay, so that is like, what if I have over here F times change in time equals your change in momentum. And my change in momentum is 200 Newton seconds. All right? It takes me 2 seconds to stop the first time, but maybe the next time it takes me 10 seconds to stop. Are those forces going to be the same? No. What's going to happen? So if you increase the time it takes to stop, what happens to the force? Good. The force is going to decrease. All right. So it says when stopping. Oh, I'm sorry. Yeah, we'll go ahead and do this and then we'll go back to this one. So when stopping, change in momentum is the same for rapid or gradual stops. Increase in the time decreases the force. So what examples demonstrate this relationship? So what are some examples that show? So think about in reality, what would be some examples that show that if you increase the time it takes for something to stop, you're decreasing the force on it. Can you think of any examples? Anybody? Okay, so stopping at a stoplight gradually versus quickly. Yes, that would be an example. What about something like, so think of things that are used to actually to increase the time it takes us to stop. So let's use a car. Talk about a car and a collision. So how about a steel car? Remember old cars? Old cars used to be like all metal. Okay. All right. Cool. What that means is that when you hit a tree, does metal give very well? No, right? It doesn't bend very much. So what happens is that means when that metal contacts something, your stop is going to be pretty much immediate. So you have a short stop time. But as far as you, that also means the force on you is going to be a lot greater. Okay, so stopping quickly, all right, but you have a lot of force. So there are times when you would have cases where there'd be like little damage to the car because it's all metal and then the person inside is all messed up, all right, broken bones and things. So steel car versus, you notice our cars these days have a lot of plastic. Okay, so versus you've got your like plastic, your a lot of like the bumpers. So what those are doing is that creates a lot of damage to the car, okay? But that also means because it damages, it crushes in, it is slowing you down, but it's taking time for you to actually come to a stop. So it increases your stopping time. It's called a crumple zone. Okay, so it's on purpose. All right, it's not just to make cheaper cars. It's actually a safety feature. Okay, so when you hit something, your car crumples in, which means lots of damage to the car, but it's better for you because increasing the time it takes to stop decreases the amount of force on you. All right, so that way you might come out with bruises and whatnot, but not a whole lot of broken bones. All right, same thing with your airbags. So versus plastic bumpers, or you can think about airbags. That's the whole point. What is this? That's increasing the stop time. So airbags. When you have a collision, the airbag comes out, but then as soon as it comes out, it starts to deflate, right? So what happens, the idea is that when you're moving forward, bag comes forward, deflates as you're moving forward, so that when you hit this bag, it is slowing down your forward motion. That increases the time it takes for you to stop, and it decreases the force on you. So plastic bumpers, what example demonstrates this relationship would be specifically plastic bumpers or airbags? What examples? It says decreasing the time increases the force, so that would be, sorry, I probably put steel car in the wrong place. So steel cars. Okay, another example would be like an egg drop. Okay, if I dropped an egg on the floor or on concrete, versus up here, you can play egg drop onto pillow, all right? So if you drop an egg onto a pillow, it's less likely to crack than if you drop it straight on concrete. Quick stop, drop it onto a pillow, all right? It takes a little bit longer to stop, all right? So that decreases the force on the egg. So those are some examples you can use. Other examples, if you can think of, go ahead and do that. All right, our last problem, it says a 65, not the last problem, we have two more. So a 65 kilogram passenger in a car travels at a speed of 8 meters per second. So go ahead and make your list. travels at a speed, and I'm going to put V initial meters per second. I still need to go back up and see, complete the other problem. Go ahead and write this down. I'm going to go back up to here. We had forgotten to do this problem. I had forgotten about it, so. All right, so I'm going to move back up. It says, what is the magnitude of the force required to stop the car? So we have our initial momentum. We were asked to solve for force. The equation is F delta T equals your change in momentum, which is your P final minus your P initial. One other number that needed to be added to this list that I forgot to put in here. It started at 22 meters per second, but we are stopping. So this is your initial velocity, and your final velocity is going to be, V final is 0 meters per second. Okay, so what'll happen is we have our, looking for force, changing this equation around, I have force, isolating what we're looking for, is going to be your P final minus P initial over your delta T. All right, so plugging those numbers in, force equals, our P final is mass times our final velocity, which is 0. So that's actually going to be 0. Minus your initial, which is the 2.97 times 10 to the 4th. I'm going to just move this up a little bit so it's out of the way. All right, and then this was all going to be over your change in time, which is 4.50 seconds. Okay, and that question comes, or answer comes out to be negative 6.6 times 10 to the 3rd newtons. Okay. It is negative. So remember, when something impacts, you're moving forward, but we're looking at the force to stop it, which is in the opposite direction of the motion. Does anyone still need this? All right, next, let's go back to the problem that's on the bottom. A 65 kilogram passenger in a car travels at, we had 65 kilograms traveling at 8 meters per second. If the passenger is stopped by an airbag, so again, we have final velocity is going to be 0. And it's stopped by an airbag in 0.75 seconds. So this actually is kind of looking at these two, all right? What happens if you increase your stop time? How much force is required? All right, so that means we have our F delta T equation equals P final minus P initial. Same as what we did here. It is asking about force, so force equals P final minus P initial divided by your change in time. All right, so plugging in your numbers. Force equals, this is mass times final velocity, which is 0. So I'm just going to put 0. Minus your initial momentum, which is 65 kilograms times 8 meters per second. And then we're dividing by our stop time of 0.75 seconds. The force comes out to negative 693 newtons. Okay, then it says, if the car does not have an airbag and the passenger is instead stopped in, so you're looking at the same information except your delta T is a lot shorter, whereas with the airbag, it took 0.75 seconds to stop. Without the airbag, meaning the person has probably collided with the steering wheel or something, 0.026 seconds. So be careful of the question. It's not asking you for the force. It says by what factor. So that means how many times, all right? So what's going to happen is you're going to go through and solve this problem. It is going to be the same way, except you're changing the time down here. So I'm going to go ahead and plug in the numbers. We have F equals 0. Initial velocity is the same, over 0.026 seconds. And this comes out to negative 20,000 newtons. Okay, but again, they are not asking for the force. They're asking about the factor. By what factor does the force increase? This was 693, and this is 20,000 newtons. So how would I find by how much it increased? The factor by which it increased. What would you do? How do I figure out? Did it double? Did it triple? You divide them. Okay, so I'm going to take the 20,000 divided by the 693, and that comes out to 29 times greater. The force on the person without the airbag is 29 times greater than with the airbag. Crumple zones, seat belts, airbags, okay, they're all for your safety. So make sure to buckle up. Okay, make sure your airbags are working properly. And keep your distance, okay? Distance between you and the car in front of you. Okay, ladies and gentlemen, are there any questions? All right, that's it for the notes. You have your assignment. Make sure you get everything turned in by the deadline.